Welcome back, MHP stats students. So what we're going to be doing today is 3.3 probability, and that is what we call the addition rule. What we're going to be going through is the bell work, and that's going to review some 3.2 conditional probability and some multiplication rule stuff. We're going to go through the objective and the central question. What is the addition rule? How does it relate to the conditional probability? How does it relate to multiplication rule or anything like that? We're going to go through the 3.3 probability. The addition rule is what we call OR probability, and we're going to go through many examples of that, then the summary, closure, homework. Let's get started. Let's not waste any more time. So these are the three examples I have for you. You can write them down. They are more than likely, and by say more than likely, I will say they will be, on your homework quiz, at least very similar examples, okay? So write them down as much as possible, and we're going to get to it. This first thing I want to say is whether or not it's independent. Two cards are selected from a standard deck of 52 cards. The first is replaced before the second card is selected. Find the probability of selecting a spade and then a jack. So first of all, I know it's conditional because it says and then. Okay, that means selecting a spade, but then afterwards selecting a jack. Okay, and it also tells us that it is being replaced. Since the card is being replaced, this means that each event is what we call independent. Why is it independent? Because if I take a card out that's out of a 52 card deck, it now becomes 51 when the card's in my hand, but then I put it back in the card deck is now 52 again. And then I take another card, the total has not changed at all. Since both draws don't affect each other, it is independent. That's the first thing. It is with replacements, okay? When I put the card back. My second step is to draw out my formula. Since this is independence, this is my independence multiplication rule formula. The probability of A and B times or equals the probability of A times the probability of B. And this is my formula. I'm going to cloud that for us. Okay. Now the third step is to actually solve the formula. The probability of selecting a spade and then a jack. Okay. What's the probability of selecting a spade? Is going to be 13 out of 52. What's the probability of selecting a jack? There's actually 4 jacks, just like there's 4 kings, 4 queens in the deck, and 4 out of 52. Now notice I have the same total because I'm putting the card back. If it was without replacement and I put the card away, then it would be dependent, and then I would change that total. But since I put the card back, the total stays the same. So what is this? This is actually going to simplify down to 0.25 and then times 0.077. So 4 out of 52 is 0.077. And so this actually equals 0.019. Sometimes Math Excel wants you to do a decimal version. Sometimes they'll want you to do a fraction version. It just depends. But most of the time, I think they want a decimal here. All right, let's go to the second one. A coin is tossed and a 6-sided die is numbered. 1 through 6 is rolled. First things first, I need to say whether or not it's independent or dependent. It is independent. Why? Because a 6-sided die has nothing to do with a coin being tossed. They don't affect each other at all. Okay, so it's independent. The second step is to write down my formula. This is going to be the probability of tossing a head, right here. Find the probability of tossing a head, and then rolling a number greater than 5. What's the number greater than 5? X is greater than 5. Okay. What is this going to look like? The probability of a heads, okay, times the probability of X being greater than 5. That is my formula. I'm going to cloud that. Okay, my third step is actually solving the formula. The probability of a heads and X being greater than 5. What is that? Okay, that means the probability of a heads, so I'm actually going to erase this. That means the probability of getting a heads, just like what I had here. What is that? That's going to be 1/2. Times probability of an X getting greater than 5. Okay, so what numbers are greater than 5 on a 6-sided die? Well, there's 6, and then that's it, right? So this is only one number that on a 6-sided die is greater than 5 out of 6 possible total numbers. So this is 1/12. Okay? And this reduces down approximately 0.083. That is my decimal. Awesome. Let's go to the next one. This one's a little bit tricky, so just pay very close attention. Suppose 70% of kids who visit the doctor have a fever, and 35% of kids with a fever have a sore throat. So what's the probability that a kid goes to the doctor, has a fever, and a sore throat? So what is this? This is the formula. The probability of having a fever and a sore throat equals the probability of having a fever times probability of having a sore throat given that they have a fever. So this is my formula. Don't get too caught up on that formula because it's actually very simple. I'm going to take 0.70 because it's 70%. I'm just going to change it into a decimal here. 0.70 and then times my 35%. So 0.35%. Why is it the case? Because 35% of kids with a fever have a sore throat. So that's the 35%. So 35% of kids have a sore throat given, right here, given they have a fever. That's what that line, this is what this line says. Okay? So I already am given the percentages. So I just need to multiply them together. This is 0.245 or roughly 25.5%. Okay? Sweet. So make sure you get all those questions down. Make sure you get the answers down. I'm going to erase. Use them during your homework quiz. Use them during your homework quiz because I'm telling you, it's going to be beneficial. The homework quiz is 5 questions, 20 minutes long, open notes as always. Please review your answers. Send any partial credits to me. Let's just say you forgot to simplify something. You maybe put a 5 instead of a 6 or something like that. Anything, maybe you forgot a negative. I don't know. You shouldn't have any negatives, but maybe you forgot a negative or something. I don't know. Anything like that, please send to me and then begin your notes. 3.3, the addition rule. How do I calculate the probabilities of OR events? Okay, and how do I determine if an event is mutually exclusive? Keep up with your homework. Make sure, I just remind you as you're writing this down, make sure you're doing your homework. Make sure you're keeping up with the online suggested schedule because that is there for you so that you don't fall behind. If you're falling behind and if you're not following along with these lessons, it's going to be very difficult for you to pick up your grade, okay? Before we get started, I love this meme, okay? I think we should be exclusive, okay? And then the girl says mutually exclusive, and they're no longer touching. Okay, so what does this mean? Well, actually, mutually exclusive events is something that we're going to talk about today. Mutually exclusive events literally means not touching, okay? They have nothing in common. So two events are A and B are mutually exclusive if A and B cannot occur at the same time. Okay, another way to write this, guys, is a lot of you are gamers probably. So think about like Halo. Halo on the Xbox is exclusive to the Xbox, right? It has no rights with it with the PlayStation. God of War has no rights with it with the Xbox. It's just the PlayStation 4. Uncharted is just the PlayStation, right? I think just the PlayStation 4. So those events are mutually exclusive events. And just in the same way, if you have a girlfriend or boyfriend, when you're broken up, you are mutually exclusive. If you are together, you can be exclusive, but it doesn't mean you're mutually exclusive, right? So think about it like that way. Here are some events that are actually mutually exclusive events. Number 1, drawing a king or queen are mutually exclusive events. Why? Because a king is necessarily not a king. A queen is necessarily not a king. Drawing a king or a heart are not mutually exclusive. Why is that? Because I can draw a king that is a heart. I can have a heart that is a king. So that, since they overlap a little bit, we say that they're not mutually exclusive because there is an overlap. So Venn diagrams often show the relationship between these events that are mutually exclusive and events that are not mutually exclusive. So for instance, when events A and B are mutually exclusive, there are no outcomes in common. So literally the probability is 0. I mean, that's really what it is. There's no outcomes in common, the probability is 0 is what we would say. So you can write this down. I think this is actually very, very beneficial if you write it down. So this right here, when the Venn diagrams are not touching, is what we call mutually exclusive events. They have nothing to do with each other. On the right-hand side, when the Venn diagrams are touching, we have what we call an A and B here. It's also what we call an overlap. Okay, this is what we call the overlap. These are what we call non-mutually exclusive events. Okay, so non-mutually exclusive events have an overlap, but if you are mutually exclusive events, that means you don't have any overlap at all, and that's what you see right here. Okay, so if you are mutually exclusive, you don't have any overlap, right? So think of it like that. Let's move on. So decide whether or not the events are mutually exclusive. So let's go through, I'm just going to show you all of them. Okay, so event A for number 1, is it mutually exclusive? Is it mutually exclusive with event B? You roll 3 on a die and you roll 4 on a die. These are what we call mutually exclusive. I'm going to abbreviate ME. Why is that? Because they have nothing in common. They don't overlap at all. A 4 is necessarily not a 3, and a 3 is necessarily not a 4, right? So they have nothing in common here. Event A, randomly select a male student and then randomly select a nursing major. You can, though, be a nursing major and a male. You can be both of these things, right? So since you can be both of those things, it is not, and I'm using my little squiggly, not mutually exclusive events. Meaning there is an overlap. So I'm going to write that. There is overlap. Because you can be a male and a nursing student. You randomly select a blood donor with type O blood, and then you randomly select a female blood donor. Well, yeah, this is definitely not mutually exclusive as well, because you can be a female with O blood, right? Absolutely. Okay, kind of getting the picture of mutually exclusive events. Let's move on. Let's kind of do a couple more. Awesome. So randomly select a jack from a standard deck of cards, and then you randomly select a face card. Well, here it is. A jack is a face card, right? So that means there is an overlap. You can have a face card and you can still have a jack. So this is, again, not mutually exclusive. They're not, they actually have an overlap. Again, if you want to write this down, they actually have an overlap. That's what makes them not mutually exclusive. Randomly select a 20-year-old student, randomly select a student with blue eyes. Again, you can have a student with blue eyes and a student who's 20 years old. Clearly, I mean, you can have a 20-year-old student and a student with with blue eyes. So that means you have not mutually exclusive. Again, there is an overlap. Randomly select a vehicle that is Ford. Randomly select a vehicle that is a Toyota. Now, is a Toyota a Ford? No. Can a Toyota ever be a Ford? No. Can a Ford ever be a Toyota? No. So this is what we call mutually exclusive. Because they have nothing to do with each other, it's also what we call no overlap. Okay? No overlap at all. All right. Let's erase this. Now that you know briefly what mutually exclusive events are, let's go to town on my addition rule. The addition rule says probability that events A and B will occur, probability of A or B, is given by this formula. Okay? And then if the events are mutually exclusive, then the rule can be simplified to probability of A or B equals the probability of A plus the probability of B. So what is this? What is the difference here between these formulas? It is this. And this difference is what we call the overlap. So this formula right here, okay, is the not mutually exclusive event. So if a formula is not mutually exclusive, you will use this one. Or if an event is not, if two events are not mutually exclusive, you will use this first one. Because then you have to subtract an overlap. I'll explain what that means. If they are mutually exclusive, you will use this one. Okay? Awesome. This rule can be extended to any number of mutually exclusive events, which means you can pretty much do as many as possible, as many times as possible. In other words, to find the probability in one event or another event will occur, add the individual probabilities now. Before, yesterday, what we did was multiply. Now what we're going to be doing is adding. Okay, we're going to be adding and subtracting individual probabilities of each event and subtract the probability that they will occur. So let's get right into it. Let's not waste any more time. Okay. You select a card from a standard deck of 52 cards. Find the probability that the card is a 4 or an ace. So I'm going to say find the probability that a card is a 4 or an ace. Now, before I actually do this, I need to decide, does a 4 overlap with there being an ace? Can an ace be a 4? You should say no. Okay, so that means there's no overlap. If there's no overlap, that means this is mutually exclusive. Since it's mutually exclusive, I'm going to be using the following formula. Probability of a 4 or ace equals the probability of a 4 plus probability of an ace. Okay, that's what it'll look like. This is my formula. Okay? So since it's mutually exclusive. So what will this look like? This actually equals, what's the probability of a 4? I have 4 4s in the deck. Clubs, diamonds, hearts, spades, out of 52 cards, and then plus I have 4 aces as well. Again, clubs, diamonds, hearts, spades. Now notice how 52 and 52, they're common denominators. I need to have common denominators in order to add them, right? So a good rule of thumb is if they're common denominators, you are doing something right. Let's just say that. If they're common denominators, you're doing something right. So what does this equal? This actually equals 8 out of 52. And this reduces down to 2 out of 13, which reduces down to 0.154. Awesome. Next one. You roll a dice. The probability of rolling a number less than 3 or rolling an odd number. Is it mutually exclusive? Can you have an odd number and a number that's less than 3? Well, yeah. So that means that they're not mutually exclusive. Why is that? Because I can have the probability of x less than 3 or the probability of an odd number. I'll show you. Watch. What this formula is going to look like is this. Probability of an x less than 3 plus the probability of an odd number minus, and here's the important part, I'll put this in blue, minus my overlap. So the probability of there being x less than 3 and the probability of having an odd number. Okay? So that is my overlap. That is my big long formula. Okay? That's my formula. So what's the probability of a number less than 3? Well, less than 3, name it out. You have 1 and 2. Is it including 3? No, it's not including 3. So it's 1 and 2, right? So since it's 1 and 2, I have only 2 options out of 6. So 2 out of 6 plus. What's the probability of an odd number? The probability of an odd number is 3 out of 6. So I'm going to do 3 out of 6. And then minus in blue. Minus in blue, I have the probability of an less than 3 and an odd number, right? So ask yourself, how many numbers are less than 3 and are also at the same time odd? Well, how many numbers are less than 3? 1 and 2. Which one of those are odd? 1. The number 1 is odd. So that means one number out of 6 numbers are also less than 3 and also odd. So one number out of 6 is less than 3 and at the same time odd. Okay? And so then we can simplify this. This is going to be 5 out of 6 minus 1 out of 6. This equals 4 out of 6, which equals 2 out of 3. And so this actually equals 0.667. That is my answer. Okay? Sweet. Sweet. This is addition rule. Notice how we're adding now? Yes? So let's move on. I'm going to erase. All right, let's go to town. A dice is rolled. Probability of rolling a 6 or an odd number. Same thing. It's not mutually exclusive because there is an overlap. I can roll 6 or I can roll, actually, no. Yeah, sorry, my bad. It's mutually exclusive. Sorry. I'm just going to town. I'm going to the jam, right? Can you roll an odd number and a 6 at the same time? No. Why? Because a 6 is not an odd number. So let's get to it. Probability of a 6 or an odd. What does that look like? Probability of 6 or odd is the probability of 6 plus the probability of odd. Do I need to subtract an overlap here? No. You only need to subtract an overlap if it is not mutually exclusive. Since it is just mutually exclusive, which means there is no overlap. Remember, they're not touching, they're broken up. There is no overlap here. That means I don't need to subtract an overlap. So what's the probability of rolling a 6? 1 out of 6. What's the probability of getting odd? 3 out of 6, because you have 1, 3, and 5. So there's 3 out of 6 here. This is 4 out of 6. Reduces down to 2 out of 3, which is also, just like the last problem, 0.667. Okay? Sweet. Next one. A card is selected from a standard deck of 52 cards. Find the probability that the card is a face card or a heart. Can you have a heart in a face card? Yes. You can have a queen of hearts, and the queen is a face card. So what does this mean? This means that this is not mutually exclusive. What does that mean? It means it does have an overlap. So probability of a face card. Probability of face card, okay? Or a heart. You know, I'll do a little heart here because I think that's cute. Okay? Equals the probability of a face card. Probability of face card. Wow. I want it to be so perfect. That's really what I want to do. Just have it be perfect. That's better. Probability of a face card plus the probability of a heart, and then minus the overlap of a probability of a face card and a heart. Okay? A face card and a heart. What will this look like? Okay? So what's the probability of a face card? The probability of a face card is actually 12 out of 52. Why do I get that? Because in each suit, there's 4 suits, right? In each suit, you have 3 face cards. You have Jack, Queen, and King. So what's 3 times 4? It's 12. So you have 12 total cards that are face cards in the deck. How many are hearts? You have actually 13. So you have 13, including the ace, 13 cards that are hearts. Subtract those that are face cards and a heart. Well, again, you have 3, Jack, Queen, and King, that are face card and a heart. So that means you subtract 3 out of 52. 12 plus 52 is 22. All over, if I do 12 plus 13 and then minus, that's actually 25, and then minus 3 is 22. So I'm going to just do it all together. So 12 plus 13 is 25, minus 3 is 22. This reduces down to 11 all over 26, which reduces down to 0.423. Okay? So hopefully you're familiar with the addition rule and the probability, how to actually do the addition rule. I personally like this a lot better than the multiplication rule. Let's get into a little bit more complicated examples, more empirical probability. Okay. So a frequency distribution, right here, frequency distribution shows the volume of sales in dollars and the number of months a sales representative reached each sales level during the past 3 years. If this sales pattern continues, what is the probability that the sales representative will sell between 75,000 and 124,999? So what we really want is kind of pinpointing these. That's what we really want. 75,000 to this. So we want 75,000 to the 124,999. Okay, so how do I do this? Well, first of all, I need to say whether or not it's mutually exclusive. And it is mutually exclusive because there is no overlap. Okay, there is no overlap between the 75,000, this event right here, and then this event because they're totally different. So what I make here does not overlap with what I make there. So it's mutually exclusive. My first event, I'm going to label this. Event A is going to be that 75,000. And we're going to have our X, our probability X, be between 75,000 and 99,999. So it's really just this part right here. Okay? What's my B? My B in blue is the other part. It's going to be the 100,000. And that's going to be between, the probability is X is between 100,000 and then 124,999. So again, these are not touching. They're completely separate, which means they're mutually exclusive. They do not have any overlap. Okay? Awesome. Let's do it in green. What does this mean? Well, my formula is this. The probability of A or B equals the probability of A plus the probability of B. This is my formula, yes? For a mutually exclusive formula. If it was not mutually exclusive, I would have to subtract an overlap here, but since it's mutually exclusive, this is my formula. Okay? So now what do? Well, I look at what's the probability of A. Well, I look at probability of A, and that is 7, right? Right here, probability of A is 7. Actually, you know what? Let me color code that so I don't confuse you. So this equals 7. Now I need to know what the total months is. The total months, I have to add these all up. So go ahead and add them all up for me. You should get a number. Your number should be 36. So when I add them all up, I get 36. So I need to have that. I'm going to add that. I'm going to add that to my blue. So probability of blue right here is 9. So I'm going to have 9 all over 36. So what does this equal? This equals 16 out of 36. Wow, I'm just messing up everywhere. 36, which reduces down to 4 out of 9, which reduces down to 0.444. And this is my probability. So this one is a little bit more complicated. It has to do with empirical probabilities, actual data being collected. And so I like to throw a couple of examples in there. Really, the hard part is just understanding that you need a total, 36. And then understanding that this is separate. These are two separate things. Okay? Let's erase and let's do some more practice. Find the probability that the sales representative will sell between 0 and 49. So 0 and 49. So now what I'm doing is going from $0 all the way to 49,000. So this part right here. So I pretty much know what to do. The probability of A or B equals, well, this is totally separate and that's totally separate. And I already know that the total of it, when I add them all up, is 36. So that means this is just 3 all over 36 plus 5 all over 36 is 8 all over 36. Take each one divided by 4. This is 2 divided by 4 is 9. And this reduces down to 0.222. So again, not that complicated, just kind of going through the motions. We have one more example left, and we have 4 parts of that example, and then we completed the full notes. So let's get to it. I don't want to waste any more time. Example 4. Yep, example 4. Blood bank catalogs the types of blood, including positive and negative Rh factors, given that the donors during the last 5 days, given by the donors, during the last 5 days. The number of donors who gave each blood type is shown in the table. So a donor is selected at random. Let's go to town and see what this means. So first of all, this is my first table. This is the table that you have right here. I give you that whole table if you're following along in the notes. Find the probability that the donor has type O or type A. Okay, so what is that? So type O or type A. So probability of O or A. Now we need to find whether or not it's mutually exclusive. Can A have anything to do with O? Do they overlap? Does O overlap with A? And we see that they clearly don't. What is an O blood type is definitely not an A blood type. So that means they're mutually exclusive. Since they're mutually exclusive, that means I don't have to subtract and overlap at all. Okay, and so my formula is probability of O plus the probability of A. What is that? That actually equals, what's the total probability of O is 184. So 184 all over my total, so 409. My total is 409. And then plus, what's the probability of A right here, 164. 164 all over the total 409. This reduces down to 348 all over 409 because I can combine because they have like common denominators. And this, when I simplify down, is 0.851. So about 85% that the probability will be that donor has an O or an A blood type. Not too bad, right? Not too bad. All right. Let's go through these next examples. Find the probability that the type owner has B blood or is H negative. Okay, so H negative. So I can have H negative right here or B blood. Now, is there an overlap? There is, which means this is not mutually exclusive, which means I do have to subtract that overlap. So B blood and then or negative. Okay, B blood or negative. That's what I'm going to do. Okay, B blood or negative. So this means this equals probability of B plus the probability of it being negative minus the probability of it being B blood and negative. Okay, what does this equal? What's the probability of B? The probability of B total is 45. So 45 out of 409. And then plus, how many are negative? 65. So I just follow my chart there. So 65 are negative all over 409. And then I need to subtract out the overlap of those that are B and negative. That's the overlap. So B and negative. And here the overlap is 8 out of a total of what? 409. So 8 individuals have a negative B type blood out of the 409 individuals. I need to take that out in order to get my true probability. So what does this equal? This actually equals 45 plus 65 minus 8. I don't like that negative here. That equals 102. And this is 409. And this simplifies down to 0.249. So about 25% of those have a type B blood or an Rh negative. Let's go to the next one, probability of B, that the donor has a type B or type A blood. Since B has nothing to do with A, this is a simple probability as this is just mutually exclusive. So probability of B or AB blood. So this is the probability of B and then plus the probability of AB. What's the probability of B? Probability of B is 45 all over 409, just like what I had in the last example, plus probability of AB. So this is 16. So 16 all over 409. And this, of course, when I add it and reduce it down, it gives me this decimal after I do all that crazy math. It's roughly 50%. So 50% roughly has a type B blood or type AB blood. Okay, let's get through one example, one more part. I'm going to erase. Let's get through one more part, and then this will be our finishing one. So probability that type has O blood or Rh positive. So positive and then O blood. There is an overlap here, so that means it is not mutually exclusive, which means I'm going to have this formula, O blood or positive. So this is going to be the probability of O plus the probability of positive, and then minus my overlap probability of O and positive. Okay, so what's the probability of O? This is going to be 184 all over 409. Probability of positive. Positive right here, 344. So 344 all over 409. Minus, what's the overlap between positive and O? It's 156. So 156 all over the total 409. What does that equal? That equals, when I plug this on the calculator, I get 0.9097. By all means, guys, use your calculators. If you haven't yet picked up a TI-36X Pro at Walmart, please pick it up. It's actually like $20. If you can't afford it, then you can use Desmos.com, because Desmos.com, you can actually plug all this in. So if you go to Desmos.com right now, and if you plugged in this fraction right here, you would get that decimal. Okay, so I'll actually show you it just because I want you guys to understand what Desmos is. So I'm going to plug in 184 divided by 409, and then I add that to 344 divided by 409, and then I minus this with 156 divided by, again, 409. Now notice I get the exact same decimal, and I can even turn it into a fraction if I want to. It gives you a fraction as well, and then if you want a decimal, boom. So this is very, very useful. Use Desmos.com if you can't afford this. Okay, it's basically, Desmos is just a free online version of this. I mean, honestly. You're going to be using Desmos a lot, like a lot in the next couple of weeks when we get to our statistics unit. But for right now, you can definitely just use this calculator. But if you can't afford that calculator, use Desmos. It works either way. Okay, but that is my answer, rounded to the 4th decimal place. Awesome. That is the summary of probability. Now, what we just did this week, guys, is literally the basics of probability in just like 3 or 4 days. I mean, we learned the basics of probability. We learned the conditional probability. We also learned the multiplication rule. We also learned just the addition rule. And what is the addition rule on mutually exclusive events, independency, and so forth. So what I have here is just a summary. You will, if you printed off the notes, or if you're looking on the key online, you'll see this on that handout as well. This is just really a summary of everything we've learned, from classical, empirical, the range of probability rule, the complementary events. We learned the multiplication rule. What does it mean to have independent and dependent events? And then we also learned the addition rule, and what does it mean to have mutually exclusive events or non-mutually exclusive events. If you have any questions on this summary page, let me know. But if you don't, then I'm going to assume that you already know all of it, or at least know most of it, okay? It is kind of confusing. You will have a quiz tomorrow, so I'm going to kind of go through that. I'm going to have a whole day tomorrow when I'm kind of reviewing during bell work your quiz. But what did you learn today? You learned to determine 2 events that are mutually exclusive. You learned the addition rule, to find probability of 2 events. And yeah, that was it. You used the addition rule to find the probability of 2 events, and you used mutually exclusive events. So you have a quiz tomorrow. You do not have a homework quiz. You have a quiz because you only have 2 quizzes in the whole quarter, and this is one of the most foundational things for probability, your unit in probability. So you need to know what probability is, all right? But because you have a quiz tomorrow, and maybe you're watching this on on Wednesday, that's fine. If you complete the 3.3 homework assignment on Math Excel at 100%, and you complete the probabilities quiz review at 100% before taking the probabilities quiz, I will give you plus 5 extra credit points towards that homework and plus 5 extra credit points towards that homework. Okay, so a grand total of 10 extra credit points on the quiz, capped at 50 out of 50, but a total of 10 extra credit points towards the quiz, which means that can actually add 20% of your grade. 20% of your grade. If you get an 80% on the quiz tomorrow and you did both assignments at 100%, that can give you 100% on the quiz. Okay? So please utilize that as much as possible. If you have any questions tonight about the quiz review, please let me know. Email me, communicate to me however you need to. But guys, it's been real. I'll catch you later on the next video where we're going to be reviewing the probabilities quiz review. We're going to have a lot of assignments, probably about like, I don't know, 5 or 6 different questions from the quiz. We're going to be reviewing that during bell work. So hope to catch you there. Peace out, stats.